You remember last lesson we looked at how the stars move around with the celestial sphere, and we looked at the fact the sun moves across the celestial sphere every year, okay? We need to move on from that and look at how things like planets move, okay? And this little plotting exercise is quite a nice way of winding down at the end of a busy day. And what it will show you is how things move across the giant glass sphere that we imagine to be around the Earth, called the celestial sphere, okay? Now, what you're going to be doing, if you just open up your pack, you will see, can you see on the first side there, you've got the stars, or the bright stars in the constellation of Leo, okay? Notice they give you two numbers for each star, one called RA and one called DEC, okay? Basically, if you think about it, I'm sure you've seen an XY graph in maths. Yeah? And you know the numbers go up the side, 1, 2, 3, and on the bottom, 1, 2, 3. And if I said x is 2, y is 1, then I think you know that's the point I'm after. Have you done that kind of thing with maths? Yeah. Have you ever played battleships?
Yes. Yeah.
In fact, if you think about it, let's just remind ourselves about Skipton. There's Skipton. Skipton is at a location of 54 degrees north, that's its latitude, and it's at a longitude of 2 degrees west, where that's obviously the Greenwich meridian. Okay? So if I've got something on a piece of paper, I can tell you x is 2, y is 1, you can find the position. If you're playing battleships on a flat piece of card, you know what you're doing. And if you want to find positions on the Earth, now think about it, the Earth's surface is actually curved. But it's still two-dimensional. So you can still, just with two numbers, this is the idea obviously of coordinates, have you heard that phrase? Yeah. X, Y coordinates work in your maths book. Latitude and longitude work on the surface of the Earth. If I give you a latitude and longitude, you can find a position on the surface of the Earth. Okay? Now what we're going to do is exactly the same thing with the sky. Alright? Now, the situation is very similar to latitude and longitude. Think about Skipton's position on Earth. 54 degrees above the equator, 2 degrees on from the Greenwich meridian. Okay? What we're going to do is basically have two similar coordinates in the sky. Okay? So keep thinking latitude, longitude. All we're doing is doing a different version in the curved surface of the sky. Okay? First of all, going up the sky, so the equivalent of latitude, we have declination. Alright? The middle of the sky is called the celestial equator at naught, and declination can either go minus or it can go plus. Okay? At the top of the sky, the north pole of the sky, it would be a declination of plus 90. At the south pole of the sky, it would be minus 90. Okay? Pretty much the same as latitude, except latitude we say north, below the equator we say latitude is south. Alright? The only difference is declination goes plus and minus, where latitude goes north and south. Okay? Right ascension is a bit different. Right ascension goes around, right ascension goes around the sky, it's the equivalent of longitude. Okay? Right ascension goes around the sky, and unlike longitude, longitude can either be a longitude east of Greenwich or it can be a longitude west of Greenwich. We don't do that in the sky. Basically, right ascension starts. Right ascension starts at 0 and goes all the way around to 24. Okay? So what I want you to do is on your piece of graph paper, I'm going to give you a piece of graph paper. In fact, they're extra large A3 piece of graph paper because you need to spread this out a bit. Okay? What I'm going to ask you to do, have a look at the first one on the first page there, which is Leo. Okay? It looks a bit different, but basically what you've got there is a set of XY coordinates. You've got right ascension, which is how far along, and you've got declination, which is how far up and down. Okay? Now, if you are going to plot, if you plot those 7 stars, then what you'll get is Leo the Lion. You'll get these stars which show you the position of Leo the Lion. So you should get something like that, showing you basically the shape of the lion. Okay. In ancient Egyptian times, could you see the constellation of Leo? Yes, you could. It's often associated with the Sphinx, because people think it's significant. Because it had pretty much the same right ascension and declination. Okay. Give me an object that doesn't keep the same position on the sky. Moon? Sun? Planets? Yeah. So the first step is the easy one. You're just plotting in the fixed stars. Remember that from last lesson? The fixed stars of Leo. Yep. Now, let me save you a bit of bother. All right. There's a couple of elephant traps in this activity, and it's a bit too late in the day for that sort of thing. So you're going to get a piece of graph paper in a minute. Up the side, you're going to put declination, like an XY graph. Along the bottom, you're going to put right ascension. Okay. However, there are two things that I can help you with. Firstly, do we need the declination to go from -90 up to +90? Well, if you scan your eyes down the figures, I think you can see that you don't need to do that. Okay? The objects I would like you to plot are the stars of Leo, the Sun, Mars, and Saturn. Don't bother with the Moon for the moment. So don't need to do all of them. And in fact, it looks a lot of work, it doesn't take you very long. I'd like to plot the stars of Leo. You should get a nice line. Plot the right ascension declination of the Sun. So the right ascension declination of the Sun will, I don't know which particular month this is, but it will change. Alright, the Sun moves across the celestial sphere. Okay? But let's just sort ourselves out with this particular bit of plotting. What's the largest declination number amongst these things? So run your eye down the declination column for the Leo, the Sun, Mars and Jupiter. Forget the Moon. What's the biggest declination value? Right, so you don't need to go up to 90. Don't do plus or minus 90 because your whole drawing will be a tiny little thing in the middle of the page. You just need to go to plus 26. What's the lowest one? It might be negative. What's the lowest declination of Leo, Sun, Mars and Jupiter? So down to about -1. So first thing, gents, don't be thinking plus or minus 90. Declination does go from plus or minus 90. This activity, you're actually only plotting quite a small bit of sky. Your declination only needs to go up to 26. And it only needs to go to -1. Now your right ascension axis, be careful, look at this. The zero of your declination is not at the bottom of the page. The zero of the declination is not at the bottom of the page because you need to be able to plot down to -1. Okay? What's the lowest right ascension you can find amongst Leo, the Sun, Mars and Jupiter? Get the Moon. Right ascension needs to start at 8. I said it goes from 0 hours to 24. You don't need to do that here. What's the biggest right ascension you can find out of Leo, Sun, Mars and Saturn? Keep saying Jupiter. So it's 8 hours to 13, isn't it? Really? 8 to 13? Now, can I just point out to you, for reasons I'll leave you to think about, you need to plot the right ascension backwards. If you plot it 8, 9, 10, 11, 12, 13, you'll get a perfect set of results completely back to front. For reasons we'll go into another time, you need to do it like this. You need to go from 13 hours down to 8. Alright, be careful with that. So 9 3/4, for example, will be there just next to 10. Okay? You need to go 8, 9, 10 up to 13 backwards. Alright? If you do it 8 to 13 like you logically do, you will get everything completely the wrong way around. Your line will be completely back to front. Okay? So basically I'm going to bring you a nice piece of A3, I beg your pardon, nice piece of A3 graph paper. Can you draw yourself a declination on a right ascension axis? Declination from -1 to 26, right ascension from 13 down to 8, and then get plotting.